this lecture, we're going to have a look at the notion of a game loop. It's the core mechanism within games in terms of controlling the evolution of the game. So how objects get to be updated and drawn on the screen. So effectively, you can sort of think of it as the heartbeat of the game. It's the rhythm that keeps it on going and going and going. But we'll have a little look at the contextual history of it. We'll do an exercise in terms of how you can design a game loop. And then we'll think about some of the more advanced aspects that would feature in most modern contemporary games. So start off first of all, a little bit of history. To do this, you need to go really back to the very first games that were published in the old 8-bit computers. Back then, there wasn't really any notion, any sophistication in terms of how this worked. Games basically ran as fast as they could. A game's an iterative process, so you check for input, you update objects, you draw things to the screen, and you fundamentally just repeat that process. For the very first games, they just ran as fast as they possibly could run. So they were written for a device, and they ran on that device at full speed. There was no notion of trying to sequence or to delay. It just went as fast as it could. In part, that's contextual because the machines back then were woefully underpowered in comparison to the ones today. So there never really was enough available oomph on the machine. So programmers were very often trying to use tricks and other techniques to get as much processing out of the machines as possible. And the other one was that there was a lot more standardization, that if you had a Spectrum or a Commodore 64 and your friend had it, well, it was exactly the same model. The clock speed didn't differ. So one game running on a Commodore 64 ran exactly the same as another game running on a Commodore 64. Rather different nowadays when we think of the computational power of the devices. Also when we think of the diversity that if we're writing, for example, an Android app, there is a very wide range of different processors and platforms and speeds on which this can run. So we need to have some mechanism to make sure that our games have the same overall play experience from one device to the next. And that's where the game loop comes in. So tying things together, early solution that they used to try to manage this was the use of a timer. So you can set up timers and platforms, and you can say that every, for example, 30 times a second, you want to receive an interrupt. You want to receive a notification that a tick has happened. And given that notification, you can have a similar process to what you see on screen. You can process input, you can update your objects, and you can render or draw them out, and you can then repeat that process. So what we have here is the most simple setup. It's along the lines of wait for a tick, do these three processes, wait for the next tick, it comes along regular intervals, and repeat it again. Simple, it often works, but can be a little bit problematic. And one of the reasons it's problematic is what happens when you do not keep to your intended schedule. So I might want to be doing, say, 30 updates and draws a second. But what happens if I get to a part of the game where I'm running some complex algorithms and that slows things down, or I have some over-the-top graphical effects, and again that's putting a greater burden on it. So games can vary in terms of the amount of work that has to be done from one frame to the next. And the approach we have outlined there doesn't scale particularly well to this. In particular, if we assume 30 updates a second is what we're targeting for, but we have a lot of fancy graphical effects, so we're not able to do this, we're only getting 20 updates per second, then the problem of the approach we have there is that it's not that the game is running at the same speed as before and the frame rate's just a bit lower, but the whole thing is running slower. We're doing fewer updates, we're doing fewer renders. And if in our update we've assumed that we will have 30 of them a second, and we're updating the position based on 30 updates a second, and we're only calling it 20 times, then other than the game being displayed slower, it actually plays slower. So the whole thing slows down and the user will not be playing the game at the speed we intended them to play it at. So this is it's not a great solution where we have situations where the total load from one frame to the next is variable. So something we can improve upon. I have a bit of an exercise here. Suggest you do it because it gives you an opportunity to think, well, how might we improve upon that? So just to break this down, so we have a couple of methods here. 4 of them is all we need to do. Let's assume we have a method called update. And if we call that method, it'll update all of the game objects that are relevant for that particular frame. We have render. We assume if we call that, it'll draw the relevant frame. So effectively, one call to update different than one call to draw it. The other 2 then get into this notion of being able to control things. We can ask the time. So at any point we want, we can go and say, give me the current time. And we will assume it will give us a time that is accurate to the nearest millisecond. That's a safe assumption. So when we get the times, we're tracking things at a millisecond range. And we have another method called sleep. And sleep, if we call it, we pass in the number of milliseconds that we want to go to sleep. So if we finish things early and we've got a bit of time left over, we can call the sleep method, and that'll basically block, it won't waste resource in the computer until the sleep time's expired. We'll wake up and we can then carry on doing things. So the challenge for you, down at the bottom, develop an approach that attempts to provide a target number of updates per second. So if I say I want to have 30 updates per second, but if I get into a situation where I'm finding that my update and my render, is not enabling me to hit my target 30 updates per second, then the corrective behavior I should take is I should start dropping some of the frames per second. So as opposed to update, draw, I might do update, draw. So I squeeze in a couple of updates, I lower the frame per second, but my target is that I try to stick to my target number of updates, and if need be, I sacrifice some of the renders to make sure I adhere to that target. And you can do that perfectly simply using these 4 different methods. So probably in the lecture, actually, we'll go through this exercise, but it's included here because I think it is a useful thought process to go through to have a ponder about how you can do this. So wholeheartedly recommend you pause this now and you actually attempt that process. It will be to your benefit, most probably. You can make it more difficult, and in fact, in reality, it is more difficult. And this comes into the some complications around the sleep method. And this applies currently on basically most devices. If I say I want to go to sleep for 3 milliseconds, so I put in a request to some simple thread on the computer that it should go and do something else. 3 milliseconds times, it should wake me up and I'll carry on processing. Now, the problem with that is that if you say 3 milliseconds, sometimes it will be 3 milliseconds. However, sometimes it'll be delayed slightly. It might be 4 or 5 milliseconds before you get woken up. Sometimes it might actually come in a little bit early and you'll get woken up after 2 milliseconds. So the sleep request often is not exact. It will be slightly out. Not massively, but slightly out. And over time, if we were to run the game, these are small inaccuracies that may balance out, they may accumulate, but you might have a situation where the game drifts a little bit from our target number of updates per second. And you could live with it, but I think it's better to try to address that, to take it into account, and to deal with these inaccuracies. So if you wanted to make the challenge in the last slide more complicated, this is a good element to combine in. So yes, overall this inaccuracy can add up to lost frames. Now, next slide I have, looks complicated, it's not really, but we'll go through it in good detail. It's an algorithm actually that can manage your game loop and can manage it in a way that does take into account inaccuracies in sleep and that does skip renders if we get behind with our target number of renders. And as you can see, it all fits quite comfortably onto one slide. So we're not talking about a massive algorithm here. So we'll go through this. The yellow box at the top highlight some of the key variables that we have in this. The first one, update period, you can see is 1000 divided by the number of updates per second. So we're assuming here that update period will be a number, and it will be the number of milliseconds that we have available on target, ideally to do our update and to draw the thing out. But that's our number of updates per second. So if we're running at say 50 updates per second, that gives us 20 milliseconds in which to do everything. Now 20 milliseconds is, in fact, it's considerably less. The blink of an eye, generally an eye, maybe a quarter to a third of a second. So 20 milliseconds is a very small period of time, but that's what we're working within. Time beyond period, initially set to 0. This is something that will track how successful we have been in hitting our target. So if it stays at 0, it means that we are updating and drawing, and we're hitting our target and everything's going fine. If that number starts to increase, it means we are behind schedule. We're actually getting behind ourselves. So if it's sitting at, say, 10, it means that we are 10 milliseconds out from where ideally we would like to be. If it gets to 50, it means we're 50 milliseconds out. So we will use this to track just how good we are by way of keeping on our target. Overtime is the third variable, again set to 0 initially. This we will, whilst time beyond period is more of a long-term track, overtime is going to be more in terms of looking at the last frame. And did we sleep in? Did we sleep for too long? Were we woken up early? Just what is the error in terms of our target for that last frame? Okay, let's have a look at the code then. So it's a while loop, line 1 down to line 21 would be the bottom brace for that. So while running, so we're going to keep doing the following thing. And lines 2 to 5 is really our bread and butter stuff. So we measure the time where we start at. We update all of our objects and we draw all of our objects. That's normally what we're going to do, update and draw. And at line 5, we measure how long that took. So we know when we started, we know when we finished, so we know the duration that that update and render actually took. Line 7 looks complicated, but we'll go through it. So line 7 is the sleep time. So okay, never introduced this. So the sleep time is a variable that determines or specifies how long we need to go to sleep for. If it's a positive value, let's say a value of 3, it means we need to go to sleep for 3 milliseconds. It can be a negative value, and a negative value means that we effectively have been we're being woken up. We don't need to go to sleep. We're behind schedule, something like that. We just need to keep on going. So no sleep is actually needed. So there's 3 elements then to determination of sleep time. First one is update period. And we're taking away from that t after minus t before, and we're taking away from those 2 elements overtime as well. Now let's think about this here. So sleep time, how long we're going to go sleep for. If everything happens instantaneously, then the maximum sleep time is our update period. So if it took 0 milliseconds to update and to draw things, and we're doing for a 20 millisecond period, then our sleep time is just 20 milliseconds. So we start off with update period. That's the maximum amount we would ever consider going to sleep for. T after minus t before is the total duration of that update and draw. So this is how long it took. So we take that away. And again, that makes sense. If we're aiming for a 20 millisecond update period, and it took 12 milliseconds to do the update and the render, then we only want to go to sleep for 20 minus 12, 8 milliseconds. Simple as that. The final one we have down there is overtime. So if we are finding ourselves that we are, for example, are getting behind schedule, then we want to take this off the sleep period for this particular iteration. So let's assume on the previous frames, our overtime was 3 milliseconds. We're 3 milliseconds out. Then for the sleep time for this frame, we will also take off that 3 milliseconds. So we'll try to wake up a bit earlier to get rid of the overtime. So line 7, we determine how long we should go to sleep for based on how long it took for that frame and whatever error we are actually carrying with us. Now line 9, we have an if, the else is down at line 13. So the if is if the sleep time is greater than 0. So if it's greater than 0, it means we actually do want to go to sleep. If it is 0 or less than 0, it means that we don't want to go to sleep. And there's two reasons why we may not want to go to sleep. Either we're spot on, or we actually are behind schedule. So we'll never go to sleep if we're behind schedule. We want to correct things. So let's have a look at the sleep time is greater than 0. So we're okay. We can go to sleep. In line 10, we go to sleep for the calculated amount of time. And in line 11, we work out what the new overtime is. So there we're asking, what is the current time? And we're taking away from that t after, which is basically when we finished. So this is how long we went to sleep for. So we finished, take away the current time. That was our actual sleep duration. And we take away from that our target amount of time, sleep time. So if overtime is positive, it basically means here that we slept in, we slept beyond our period. If it's negative, it means we've woken up a little bit early and we're a little bit ahead of schedule. For the else statement down, so lines 14 to 18, this is basically the bit where we are behind schedule. So what activities do we do? In line 14, we update our time beyond period. So we are taking away sleep time, but sleep time will be a negative value, so effectively we are adding a positive value then onto time beyond period. So we are accumulating how far overall we are behind. So if we were previously 10 milliseconds out and the last frame we missed it by 2 milliseconds, we will update our time beyond period to be say it's 12. We're now a total of 12 milliseconds out. And we set overtime to 0, so we just null it at that point. Line 16 is the interesting one. So whilst time beyond period is greater than the update period. So let's assume our update period is 20 milliseconds and our time beyond period is 10 milliseconds behind. So we're half a frame out, doesn't matter, we just carry on. As soon as we get one frame behind, so as soon as time beyond period is greater than the update period, we take corrective action. We say at that point, hold on, we're now one frame behind where we want to be. So we're going to try to do something about it. What we do is line 17 and 18. We do an update, but we don't draw it. So we just update the world, but we don't draw the thing out. So this is our way of trying to save a bit of time of dropping a render, but just doing an update because we should have done an update. We're an update behind, so let's get that update out of the way. Line 18 is where we make a correction. So we take off one update period from our time beyond period. 16 to 18 is part of a while loop. So if we are massively behind our schedule for whatever reason, then we will do a number of updates until we think we've got caught back up with ourselves. And then we carry on. An obvious implication of this is that, if we think about getting behind, a couple of reasons. Either our update is taking too long or our render is taking too long, or the combined elements, both of them together, are taking too long. So the approach we have here doesn't work if fundamentally it is the update that is breaking the bank, that is taking longer than anticipated. It only works if the render, if we drop it, means that our update then can be done on schedule. So there is an assumption here about the type of world with which we're operating. For more advanced looping structures, a couple of things we want to look at here. The previous example, I think we assumed a 20 millisecond update period, so it was fixed. And if we called our update method, effectively those objects could assume that it would be called at regular intervals. That's one way of doing it. Another way of doing it is to have a variable step size. So sometimes when you update objects, you're saying, I want you to update yourself, and 5 milliseconds has happened since the last time you update yourself. And then after that, I want you to update yourself, and 7 milliseconds has happened. So you pass in a variable that tells them what is the delta, how much time has elapsed from it. So this again makes it a little bit more straightforward. You run the update and the render as fast as you possibly can, and you just basically pass in a variable that says, well, X number of milliseconds have elapsed from it. You don't get anything for free. It does, and it can make the updates of the objects more complicated because they can't simply assume every single step will be of the same duration. They have to look at what the actual step time was, and then to take that into account, for example, for movement, for rotation, for anything where time is an element of the update. So elapsed time, delta step values passed to each update and draw. More ticks on a faster machine, so you have a smaller number of updates. And on a slower machine, you have a smaller number of updates with a larger delta value between them. The final bit we want to look at there in terms of more advanced techniques is the whole multi-threaded aspect. That reality is nowadays everything is multi-core, and the update loop we previously identified is really a single threaded process. Sure, whenever you're calling update and whenever you're calling render, you can have as much threading within those different methods that you want, but our world view within the game loop was single threaded. And that's not ideal because effectively we have a linear process. We update and we draw, we update and we draw. So whilst we are drawing, we're not updating, and whilst we're updating, we're not drawing. So we're not necessarily maximizing the amount of parallelism that we have available. This actually is important because generally there's two chunks of silicon for the CPU and the GPU. So the bits that do the update quite often are different than the bits that do the rendering. There's a way of getting around this, and you can see it down at the bottom here. Ideally, we should be updating the world for time t. We should be drawing the world. So at time t, we want to draw the world out for time t. And at the same time, we want to be running our update processes for time t plus 1. So we're planning for the future and we're drawing the current state. And then we have a swapping phase at the bottom where our planning gets wrapped into the current world. So in this case, we can do planning and drawing effectively concurrent at the same time. And that's a more efficient way of utilizing quite often the types of devices that we're using. Little bit here just in terms of us for this course, because the game loop is the fundamental mechanism we have within games. The notion of updating an object and drawing it is well established. And whenever you're thinking about your objects, you will want to think of them in terms of an update and a draw or a render. So in designing them, decouple these two processes. Ask two separate questions. How do I update this object? How do I draw this object? And make sure there's a clear distinction or divide between those two elements. So for example, if you had an animation, the frame of the animation that you should be choosing is what you decide in the update. And when you're drawing it, you just draw it out with that frame of animation. It's good to do that because if you didn't, if when you draw it out, you included the calculation for how much time has elapsed and what's the appropriate frame, and you put it into the draw code, you might think, okay, it works fine, until you go to try to pause the game. So quite often when you pause the game, there are elements you will still keep running, but you're going to sort of, the update, there's elements you will pause, but for the rendering, you want to keep that ongoing for whatever effects it is. So it will make it more complicated if you don't have that separation. So the draw phase should not change the game state. That keeps it clean, it keeps it simple. So properties of objects and so on, it should simply visualize the game state. And if you adhere to that practice, it will simplify your design overall. So takeaways from this, getting a smooth number of updates per second is a bit fiddly, but generally not too bad. To be fully effective, the game loop needs to support multi-threading. That's a reality nowadays. You can do it if you want it. It'll be worth bonus marks in terms of your design. Final point, and this is important, when designing game objects, make sure you do properly decouple the update and the render behaviors.